In this video, we are going to discuss mole conversions, and by this time you should have already completed the activity with the popcorn kernels where you look at the concept of a mole, but now we're going to take some notes and record some actual definitions and talk about why the mole is useful to scientists. So first of all, the mole is the SI base unit for measuring the amount of a substance. So when we say SI base unit, base units exist in that scale of metric units. The King Henry died by drinking chocolate milk, and by, that part in the middle, that's the base unit, and mole is a base unit. So we can add the prefixes kilo, or deci, or centi, and we can have centimoles, or millimoles, or kilomoles, and all sorts of different prefixes because this is just a base unit. But 1 mole, a single mole, is equal to 6.02 times 10 to the 23rd particles. And this is a super important number in science, especially in chemistry, the number of particles in 1 mole. This number is known as Avogadros number. And this number for a mole is 6.02 times 10 to the 23rd. It can be the number of particles in a mole, the number of atoms in a mole, or the number of formula units in a mole. And a formula unit is just the simplest or kind of reduced formula for an ionic or a covalent compound. So we talked about particles and atoms before. Formula units is the one that's sort of new, but it kind of just means the same thing. It's the number of times you have the chemical formula. And scientists define all sorts of units, and units are just made up by people, but the way that we defined the mole is we said that 1 mole is equal to exactly the number of carbon-12 atoms that is in 12 grams of pure carbon-12. So that might seem kind of nebulous, but it doesn't really matter because the mole is super useful to scientists all over. Let me move this up for a second. Let's talk about why the mole is useful. So the difficulty here is that the single atom is really, really tiny. A single atom has a really, really tiny mass or volume, and so it's a lot easier, instead of trying to measure the mass of that super tiny thing, it's a lot easier to measure a whole group of atoms at a time. And so we group atoms and molecules or formula units, we group them into these groups of 6.02 times 10 to the 23rd things, and we call that number a mole. And instead of measuring the mass of 1 atom or 1 molecule, we measure the mass or the volume of 1 mole of particles. And we call that value, for mass at least, the molar mass. The molar mass is just the mass in grams of 1 mole of any pure substance. Pure substances can be molecules, or atoms, or elements, or compounds, so any pure substance. So to know these values, it's really important that we can know the mass of a mole so that we can make conversion factors and perform conversions between moles and particles. We might want to know how many particles are in 2.3 moles, or we might want to know how many grams are in 2.3 moles. And so we have to be able to make conversion factors to get from one unit to another, and to know these values for moles and gram conversions. For atoms, we just look at the periodic table. The periodic table has all these different values for mass on it. You notice they're up here with all these decimal points. So the one for, those things kind of hard to see. Let's look at cadmium. Has a molar mass of 112.41. And then, let's see, carbon up here has a molar mass of 12.011 grams per every 1 mole. So we can use those values to create conversion factors. So carbon, we just talked about, it's our example here. 1 mole of carbon is equal to 12.011 grams. And since we know these two things are equal, we can make this into a conversion factor. We can have 1 mole of carbon on top with 12.011 grams of carbon on the bottom. Or we could flip that over and we could have 12.011 grams of carbon on top and 1 mole of carbon on bottom. Both of these are valid conversion factors because we know that 12.011 grams of carbon is exactly equal to 1 mole of carbon. So that makes it pretty easy for elements. You just look at the periodic table to find how many grams there are in 1 mole of a substance. But if we want to know the molar mass for a molecule or a compound, it takes one more additional step. We have to take the masses on the periodic table and we have to add them up for all of the atoms in the compound. So for example, let's look at water, H2O, dihydrogen monoxide. In water, there are 2 hydrogen atoms and 1 oxygen atom. So I have hydrogen, I put that there are 2 of those. Oxygen, there's 1 of those. And then I went and looked at my periodic table to find the mass of each thing. So hydrogen is 1.0079 grams, and then oxygen is 15.999 grams. And you can use your periodic table to find these values as well. So since there's 2 hydrogens, I need to do 2 times that 1.0079 grams. And then oxygen, I need to do 1 times 15.999 grams. And since these values are so close to a whole number, I'm going to round my final answers. In general, if you have 0.00 or if you 0.99, it's safe to round to a whole number. Otherwise, you ought to hold on to at least 2 or 3 decimal places. But so I rounded 2 times 1 is approximately 2 grams, and then 1 times approximately 16 is 16 grams. And then I just added these 2 things up. 2 plus 16 gives me 18 grams. So now I have 1 mole of water is equal to 18 grams, so I can write my conversion factors. 1 mole of H2O over 18 grams of H2O, or I could flip it over and put 18 grams of H2O over 1 mole of H2O. So please do notice that when I'm doing these conversion factors, it is important that you have both a unit and a substance. So I have 1 mole, mole is my unit, and carbon is my substance, over 12.011 grams, grams being the unit, and carbon being the substance. If we said that 1 mole of carbon is equal to 12 grams, that's not necessarily true. What if we were 12 grams of what? 1 mole of carbon is not equal to 12 grams of oxygen. So we have to identify what substance we are talking about. So we always need to check that we have a number, a unit, and a substance on all of our values when we are making mole conversions. Last but not least, before we flip over and do some examples, I wanted to review the diatomic elements. Diatomic elements, remember, are the pure elements that form molecules consisted of 2 atoms bonded together. So basically what that means is that these elements never truly exist in nature by themselves. They always exist in a pair. Hydrogen can be found in a compound as just 1 hydrogen, like you could have hydrogen monoxide, HO, but when it's by itself, when it's not in a compound or a molecule, it has to be paired up with itself. So in that way, it actually is always in a molecule. It's in a molecule of 2 hydrogen atoms. And the diatomic elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And this is something that you are expected to memorize and know. Do look at your periodic table and notice that hydrogen is kind of on its own by itself, but then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine make an L shape on your periodic table. So that does make it a little bit easier to memorize. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, they make this nice L shape on the periodic table. So the trickiest part about doing mole conversions is knowing where to go next. So this little chart here is useful for helping you make decisions about what conversion factor you need to use to make your conversion. So for instance, if you were given grams of something, then you first need to convert that into moles. And then once you have it in moles, you can go to either liters or atoms. So let's say we were given a conversion that said we should convert grams of carbon into liters of carbon, which that wouldn't happen because carbon is not gaseous. So let's do grams of helium into liters of helium. So we'd first convert our grams of helium into moles of helium. And then once we have that moles of helium, we do another conversion factor to convert to liters of helium. Or let's do another one. What if we wanted to go from atoms of helium to grams of helium? we'd first convert our atoms or our molecules into moles of helium, and then we'd convert moles into grams with our second conversion factor. So each step along this chart tells us what we need to use to make that conversion. So to convert atoms into moles, for instance, we need to use 6.02 times 10 to the 23rd, which is Avogadros' number. To convert moles into grams or grams into moles, we need to use the molar mass of the substance. So let's look at a couple of examples. And I have my mole chart right here to help me decide how to make my conversions. So this first example says how many grams of neon are in 7.85 moles of neon. So whenever I start a problem, I start by identifying my given value, unit, and substance. So I'm going to underline it. I have 7.85 moles of neon. And I don't want to write this whole thing out, so I'm going to abbreviate that. I'm going to put 7.85 moles, the abbreviation MOL, and then neon's chemical symbol, NE. 7.85 moles of neon. So that's my given value, unit, and substance. So now I need to figure out where I need to get to. So the problem says how many grams of neon. So I'm going to put a squiggly line under that so I know that's where I'm trying to get to. So now I'm going to look at my mole chart. I'm going to say, okay, I'm starting at moles of neon, and I need to get to grams of neon. So I need to go from here to here. That's just one step, so I'm only going to need one conversion factor. So I'm going to multiply by that one conversion factor. And in my chart, it reminds me that I'm going to be using the molar mass to make this conversion. So now it's just dimensional analysis as always. So whichever unit I want to cancel and whichever substance I want to cancel is going to go on bottom. So since I want moles of neon to cancel, I'm going to put that on the bottom. Moles of neon. And then on the top of my conversion factor, I'm going to put the unit and substance that I'm trying to get to. And this time I'm trying to get to grams of neon. So I'm going to put grams of neon on top. Now I just need to find some numbers to put in my conversion factor. And to find those numbers, we look at our periodic table. So I need to know how many grams of neon there are in 1 mole of neon. And looking at my periodic table, it says that there are 20.180 grams of neon per mole. So I'm going to fill that in, 20.18 grams of neon for every 1 mole of neon. So now I have my conversion factor set up. So now I just need to solve my problem. So I'm going to put equal sign. And we need to make sure our units are canceling correctly. So I see I have moles of neon, and I'm going to be left with grams of neon, which that is what my problem's asking for. So I have set this up correctly. So now I just need to multiply this out using my calculator. So when I plugged this into my calculator, everything is in the numerator. So I put 7.85 times 20.18, and that gave me 158.413. So I do need to pay attention to my significant figures when I do this, and I noticed that my first given value has 3 significant digits, while my second, well actually this is not a given value, this is a molar mass. So my value has 3 significant figures, so my answer also needs to have 3 significant figures. When you are doing these calculations, molar mass does not count as towards your significant figure rule because molar masses are considered to be exact values. So we're going to round this to 3 significant digits. So 158.4, so 158, this is my third sig fig, so I'm going to round to this place. So I'm going to put that it's approximately 150, and then this 8 is going to round down to 8. 158, and then of course I need to keep my units, so grams of neon. Grams of neon. Now that I have my answer, I'm going to box it in so somebody looking can find it easily. 158 grams of neon. Moving on to the next one. Let's move this up a little bit. It says how many liters of gas are in 82.3 grams of argon gas? So In this one, we are given 82.3 grams of argon gas. So I'm going to go ahead and write that given value, unit, and substance out. 82.3 grams of argon, AR. Okay, and now I need to figure out where I'm going. So how many liters of gas? So it doesn't specify here that it's argon gas, but since the only gas mentioned in the problem is argon, I know it has to be argon gas, liters of argon, so I'm going to fill that in to remind myself. So I'm trying to get from grams of argon to liters of argon. So on my chart, I'm going to find grams of argon and liters, and see, that's going to be 2 steps. So I'm going to need 2 conversion factors to get from grams to liters. First one goes from grams to moles, and the second one goes from moles to liters. So we can set this up. Our first conversion factor times our first conversion factor. Grams of argon needs to cancel, so I'm going to put that on bottom. And we first want to go from grams into moles. So this is going to take us to moles of argon. Then our next conversion factor, we want to go from moles to liters. So moles of argon needs to cancel, so we're going to put that in our denominator. And we're trying to go to liters, so I'm going to put liters of argon up in the numerator. So to get the number of grams that are equal to a mole of argon, I need to look at my periodic table. So if you look at argon here, it's 39.948. 39.948 grams of argon per 1 mole of argon. And then here I need to use this value 22.4. 22.4 is the molar volume of a gas, and it is only used for things that are gases. So 22.4 moles of, 22.4 liters of a gas is equal to 1 mole. And there's some scenarios where this isn't necessarily true. This is true of something called ideal gases, but we'll talk more about gases later. Just know for now that 1 mole of any ideal gas is equal to 22.4 liters. So 22.4 liters is equal to 1 mole. So now I'm going to go through and make sure my units cancel correctly, so then I can solve my problem. So I have grams of argon canceling out with the grams of argon down here, and then I have moles of argon canceling out with moles of argon. So then I just need to plug some things into my calculator. So I have 82.3 times 22.4 is on top, so times 22.4. And then I need to divide by the part on the bottom, so divided by 39.948. 39.948. Then hit enter, and that gave me 46 point, a bunch of decimal points, 46.1479929. I'm not going to write that all out. I'm going to look at how many significant figures I need. And I notice that my given value has 3 significant figures, so I just need to round this to 3 significant digits. So 46.14, this 4 is going to make it round down to 1, so I'm just going to have my answer as 46.1, and my units are liters of argon. And then I'm going to box my answer in, so it's easy to find my answer. And then our last problem here, let's look at this last one together. It says how many moles of nitrogen gas are contained in 65.8 grams of nitrogen gas. So, we first need to identify our given value, substance, and unit. So it's 65.8 grams of nitrogen gas. Okay, so I'm going to write that down. 65.8 grams and nitrogen gas. So it's important that as soon as you think see nitrogen, you think, ding, 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 this is a diatomic element. Hydrogen, H2, N2, O2, F2, Cl2, Br2, and I2 are all the diatomic elements. So nitrogen gas, pure nitrogen gas, is not going to exist as just a single nitrogen atom. It's going to be nitrogen bonded to itself. So it's not just going to be one nitrogen, it's going to be 65.8 grams of N2. So that's my starting value, unit, and substance. And I know I'm going to have to multiply by at least one conversion factor. I need to get to moles of nitrogen gas. I'm starting with grams, so from grams to moles, that's just going to be one conversion. So I'm going to put my conversion factor. I want grams of nitrogen gas to cancel, so I'm going to put grams of N2 on the bottom. And then I want to get to moles of nitrogen gas, so moles of N2 goes on top. Now I just need to figure out how many grams of N2 equals a mole. So on my periodic table, I have the mass of one nitrogen atom, 14.007, but I need the mass of N2. So I need 14.007, that's equal to 1 nitrogen, but I need N2's mass, so I need to multiply this by 2. And when I do that, I get 28.014 grams. So this is the number of grams that equals 1 mole of N2. 14.007 is the number of grams that equals 1 mole of just nitrogen, N. But you never really find just nitrogen. It always comes as a pair. So 1 mole of N2 is equal to 28.014 grams of N2. Now we just make sure our units cancel. So grams of N2 cancels with the grams of N2 down here. We're going to be left with moles of N2. So we just need to plug into our calculator. So we have 65.8, and then we don't need to do times 1 because that's just going to be 65.8. So all we need to do is 65.8 divided by the part on the bottom, divided by 28.014. And that gave us 2.3488255, a whole long number, but I know by looking at my given value that we're going to round to 3 significant figures. So this is going to be rounded to 2.3, and then because there's an 8 next to this 4, the 4 will round up to a 5. And then my units are moles of N2. Now I'm just going to box my answer. And that's the end.